Today's lesson, Kc and Kp. What are those? Let us have a look. Kc is equilibrium constant in molar concentration and Kp is equilibrium constant in partial pressure. In this lesson, we are going to learn Kc and Kp in detail. So, let's begin. Let us start from law of mass action. Let us consider a chemical reaction A plus B. Then product or products. A chemical reaction in which A mole A and B mole B form products. In this reaction, rate of the reaction will be proportional to the product of the concentration of the reactants. Coefficient of A and B is the coefficient of B. Coefficient of A will be as power and coefficient of B will be as power. Simply, rate of the reaction will be directly proportional to the product of the concentration of the reactants. What is the rate of reaction? The change of concentration of reactants per unit time is rate of reaction. So, rate of reaction is directly proportional to the product of the concentration of the reactants. When the components are in gaseous state, then rate of the reaction will be directly proportional to the partial pressures of the components. A is the coefficient of A, which will be as power. B is the coefficient of B, which will be as power. So, rate of the reaction is directly proportional to the product of the partial pressures of the components when the components are in gaseous state. So, rate is directly proportional to the active masses of the components. Active masses mean molar concentration of the components or partial pressures of the components. Then, what is law of mass action? Law of mass action is defined as at constant temperature, the rate of any chemical reaction at any instant is directly proportional to the active masses of the reactants. Active masses mean concentration of the reactants or partial pressure of the reactants. This is law of mass action. Now let us see equations for Kc and Kp. Let us consider a reversible reaction. This is a reversible reaction, not irreversible reaction or not one-way reaction. This is a kind of reversible reaction in which reactants convert to products and product converts to reactants. This is characteristic number 1. Characteristic number 2, rate of forward reaction equals rate of backward reaction. Characteristic number 3, concentration of any component concentration of any component will not equal to 0. Concentration of no component will be 0. These are the basic characteristics of a reversible reaction. Here, A moles A react with B moles B. Then C moles C and D moles D are formed, in which rate of forward reaction is proportional to the concentration of A and concentration of B. Coefficient will be as power. This coefficient will be as power. Then rate of forward reaction is equal. A constant term will be here, that is suppose K1. Then concentration of A, concentration of B. This is equation for rate of forward reaction according to law of mass action. Now, rate of backward reaction is proportional to the concentration of C, rate of backward reaction, and here this is rate of forward reaction. Rate of backward reaction is directly proportional to the concentration of C and concentration of D. Coefficient will be as power. This coefficient will be as power. Now, rate of backward reaction is equal to a constant term, concentration of C into concentration of D. Now, we know that for reversible reactions, rate of forward reaction equals rate of backward reaction. Then from here we can write rate of forward reaction is equal to rate of backward reaction. Then we can write K1, this equation, concentration of A into concentration of B is equal to K2, concentration of C into concentration of D. Third bracket indicates concentration of component. From this equation we can write K1 by K2 is equal to this one, concentration of C, concentration of D divided by concentration of A, concentration of B. Here K1 constant and K2 constant. Now we can put here a new constant which is called equilibrium constant. This equal to, we can write concentration of C, concentration of D divided by concentration of A, concentration of B. Here this is known as equilibrium constant and this reaction is known as equilibrium reaction, which is according to law of mass action. Now let us see equations for Kc and Kp. This equation is known as equilibrium equation, in which here we can write Kc is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. Here equilibrium constant is converted to Kc, which is known as equilibrium constant in molar concentration. When the components are in gaseous state, then we can write Kp, which is known as equilibrium constant in partial pressure. Kp is equal to, we can write partial pressure of C. C will be as power. This coefficient will be as power into partial pressure of D, here D, divided by partial pressure of A into partial pressure of B. This is equation for Kc and this is equation for Kp. Kc is equilibrium constant in molar concentration and Kp is equilibrium constant in partial pressure. These are equations for Kc and Kp. Now let us see values of Kc and Kp. Firstly, values of Kc. From this equation, we can write according to law of mass action, concentration of C into concentration of D divided by concentration of A into concentration of B. As this is reversible reaction, concentration of any component cannot be zero. Here, if we consider concentration of the products is zero, then A, B, then value of Kc will be zero. When concentrations of products zero, then value of Kc will be zero. But we know for reversible reaction, concentration of any component cannot be zero. So value of Kc cannot be zero. Again, Kc is equal to, we can write concentration of C into concentration of D. When this is one-way reaction, only in that case concentration of reactants will be zero. As we know, concentration of any component cannot be zero. So Kc in this case will be infinity when concentration of reactants will be zero. But concentration of reactants cannot be zero, value of Kc cannot be infinity. Simply, concentration of reactants cannot be zero, value of Kc cannot be infinity. Concentration of products cannot be zero, value of Kc cannot be zero. So value of Kc cannot be zero and cannot be infinity as well. Now let us see values of Kp. Values of Kp. Equilibrium constant in partial pressure. When these components are in gaseous state, then Kp is equal to, we can write according to law of mass action, partial pressure of C into partial pressure of D divided by partial pressure of A into partial pressure of B. When product of the partial pressures of the products is zero, then we can write Kp is equal to zero. But as this is reversible reaction, partial pressure of C and partial pressure of D cannot be zero. So here value of partial pressure of C into partial pressure of D cannot be 0. So value of Kp cannot be 0. Similarly, from this equation we can write partial pressure of C into partial pressure of D divided by partial pressure of A into partial pressure of B. As this is reversible reaction, partial pressure of C, partial pressure of D. If we consider product of the partial pressures of A and B is 0, then Kp will be infinity. But partial pressure of A cannot be 0, partial pressure of B cannot be 0. So Kp cannot be infinity. At a glance, Kc and Kp cannot be 0 and cannot be infinity as well, because Kc and Kp involve reversible reaction, not irreversible reaction. Kc and Kp involve reversible reaction in which there is existence of all components. Concentration of any component cannot be 0. As a result, value of Kc and Kp cannot be 0 and cannot be infinity as well. This is all about Kc and Kp. No more today. Thank you very much.